Yep.
Great, thank you. Okay, it still looks like we're missing two, but I want to go ahead and get started. First thing I'd like to do is go through a couple of administrative things. Hopefully this does not apply to you, but if you do need to withdraw from any course or lab from the fall semester, the deadline is this Friday, 2 days from now at the close of business, or by the close of business. So if you do withdraw from anything, just be careful as to how that might impact your ability to graduate in May. But hopefully nobody's having to withdraw from anything. I've had the sign-up sheets on my door for the virtual professional society meetings next week on Tuesday for the American Society for Non-Destructive Testing. Excuse me, Tuesdays for the American Nuclear Society and Wednesdays for the American Society for Non-Destructive Testing. I plan to attend both. So far, I've only had one student sign up for both. So there's one student going to each. If you are interested, please get that information back to me by close of business on Friday so I can send the names in. They will again send me, as they've done in the past, they'll send me the Zoom links either late Monday or early Tuesday. And then for anybody that signed up, I'll forward them on to you. I'm still missing release forms. I haven't gone back through my spam folder yet to see if anything's been trapped. But I'm still missing the release forms that you need to sign and return to me before the URI trips next week from Elisa, Noah, Evan K., Joel, and Quinn. So if you've already sent them, I'm going to root through my spam folder or whatever later today, sort of catch that up. I'm still missing 11 plans of study from folks, and I still have 3 of you that have not registered for the spring yet. I have 2 course substitution forms completed and into me. I'm not really sure how many of you need to do those because I don't have all the plan of studies returned to me. But if you had to substitute anything, particularly it involves things like substituting concepts of chemistry for general chemistry 1, I do need that form. I'm hoping on Monday of this coming week to have reviewed and signed off on all your plans of studies, and I hand deliver them down to the registrar so they can start the graduation audit process. So if there are any perceived shortcomings, they can get back to you before the spring semester starts so you can correct anything that might need correcting. I also plan to turn in on Monday, the same time I turn those in, I want to give to the dean all of the course substitution forms that I've reviewed and signed off on. And again, he tends to be more generous when he's looking at a group of them rather than if they sort of dribble through one at a time. Looking ahead for the rest of the time between now and Thanksgiving, we have class today, of course. I'm going to give you 2 quizzes that'll be due on Monday. We have class on Monday. We have class on Wednesday of next week. And of course, Tuesday and Thursday are URI lab days. So I already sent out the list earlier with all the information about URI, what the labs are going to be doing. But roughly half of you are going on Tuesday, half of you are going on Thursday. I'll discuss that a little bit more this coming Monday. And then the following week, the week of Thanksgiving, on Monday right now, I plan to have class. And my thinking is I'm going to have in-class exam number 3 for nuclear material science that I'll give to you, and you just turn in before you leave that day. And I'll also give to you the take-home exam number 3 for reactor theory. And that one will be due after the Thanksgiving break. That's a much more comprehensive exam. As I said before, if you've really been keeping up on things, my guess is it's going to take you about 5 to 7 hours to do it. If you haven't been keeping up on things, obviously it'll take you longer, but you have over the holidays. I've always called it the turkey leg exam because a lot of the exams I used to get back in person would have cranberry sauce stains, turkey stains all over them, but now everything's virtual, so I'm not going to have the stains on them, but I still call it the turkey leg exam. I can, depending on what else you might be having exams in before Thanksgiving, like Calculus 2 or Professor Lance's class, I could potentially move the nuclear material science class, exam back to Wednesday of next week. But I prefer to leave it on that coming Monday. Since they have shifted the labs around at URI, the lab we've done second trip. Question? Sure. Saturday did not know about it. Okay. Okay. Right now, I don't plan to be here. Saturday is, as you may or may not know, way back when I graduated from the Coast Guard Academy. A couple of my good friends that I played golf with went to the Merchant Marine Academy, and they have something called the Secretary's Cup for the Secretary of Homeland Security. And they have a football game every year that is either at Merchant Marine Academy on Long Island or here. This Saturday it's here, and I'm planning to go to that game with some of my friends, so I will not be here on Saturday. But you could chat with me later today after class, or you could drop your registration off in the box, or you could even write it up and send it to me as an email. Okay, I think it's in your best interest not to go down to the registration day because they have a lot of outside help that comes in that doesn't really understand the nuclear program or the nuclear plan of study. And I wouldn't want them to inadvertently mislead you or misadvise you. Okay. And again, depending on what you might have for Calculus 2 or Professor Lance's exam, I might consider moving the in-class nuclear material science exam to next Wednesday. But I am going to have to do a little bit of teaching I hadn't planned on doing because the labs we're going to be doing at URI for the first week are usually ones that we do a little bit later. And so at this point, you do not, and they do some teaching when you're there, but I have to make sure you know what reactivity is. I have to make sure you know what reactor period is before we go on those trips next week. Chris, did you have a question?
Yeah, it's kind of a two-parter. The first part is concerning the course substitution form.
Yes.
If I took concepts of chemistry like in the past,
Yes.
do I need to fill out one of those forms regardless of when I took it?
Yes.
Okay. And second of all, where can I find the form?
They're in the box outside my door. If people let me know who needs it, I could try to scan one in and send it to you. It's It's a fairly simple form. Basically, everything that's on the plan of study, every course, you have to take that course, you have to pass that course in order to graduate. The only other requirement is when you add everything up together, you must have a GPA of at least 2.0. And a 2.0 is a straight C. So if you took every course and lab on the plan of study, and you got a C in everything, but let's say you got a D in one course, you have passed everything, but that would not average out to 2.0, so you would have to take something else to bring that D up. That was just sort of a little bit of a side. But anything else that's on there, usually the two problem areas are, if you didn't take General Chemistry 1 with lab, you took Concepts of Chemistry with lab. And those are routinely signed, but they are variation from the plan of study. The second one tends to be the electrical course or lab that you're taking this semester. If for whatever reason you don't pass it, you withdraw from it, whatever, you do have to make that up. That specific course is not re-offered in the spring. There are two other courses that are available. One is digital electronics, and the other one is I think it's called basic circuits. But anyway, your only option then to graduate in May is to take one of those two. And when you do that, you have to use a course substitution form because you're not taking the course and lab that you're taking right now, which is specific to the plan of study for nuclear. On occasion, you might have a course, you might have, I'll just invent something, writing for engineers that you took at a different college or university, and you had to transfer it back in here. That does not have the same exact title as our required technical writing. So, and you must take technical writing, but you can ask for a course substitution by asking that course be considered. Typically, if you do something, you send along a syllabus from that course for whatever college or university that you took it at with the form, and as long as it's not too outlandish, the dean normally approves it. Anything else on any of those topics before I get started today? I'll get together with you at the end of class today to sort of lock in when we're going to do exam number 3 for nuclear material science.
Is it possible for you to scan that form and send it out?
Course substitution?
Yes, please.
But yes, I could do that I guess I could do that later today. And since I don't know who needs it, I'll just send it out to everybody. Okay. Any other quick questions before we get started? Okay. I'd like to do the Reactor Theory quiz number 13. Before I do my solution for extra credit, does anybody want to venture forth and share their solution? Nobody. Wow. Okay. I must admit, I looked at a couple of the solutions that you'd sent in earlier today, and most of you got the first part right. I don't think anybody got the second part right, but we're going to go through that right now. Okay. So we're using our same beryllium, uranium-233, uranium-238, and you might look at some of the things that we already know about this. We know that K-infinity was 1.62. The buckling was 0.206 centimeters to the -1. And remember, for buckling, everything we've done thus far that took place looking at the materials in K-infinity, we looked at buckling squared was K-infinity -1 over L squared, where L squared is the thermal diffusion length squared. Again, the thermal diffusion length is the distance a thermal neutron travels between when it became thermal to when it gets absorbed. Okay. And this B squared is based on the materials. Then later, we took the rate of change for the neutron with respect to time is 0 for steady state. We looked at production minus loss. And we developed the general diffusion equation. And while we were doing that, we also developed J, which is the neutron current density. And we had to do this to account for leakage. So when we did all of that, the general diffusion equation came out to be del 2 flux plus buckling squared flux equal 0. Okay? This equation is good for any shape. So it doesn't make any difference if you have infinite slab, rectangular solid, a cylinder, a sphere, you name it. This is the general diffusion equation that works. And then what we need to do we then solve this equation for a particular shape. So when we took this equation and we said, okay, we're going to take the materials that we had from our beryllium and the 2 uranium fuels, and we're going to put it in an infinite slab. Okay. As soon as I tell you infinite slab, you know, or you should know, depending on how your math is that this del 2 operator is exactly equal to this. Because for an infinite slab, only x is a variable. If you remember, if this is the center line, if we put the fuel in, the fuel and moderator in this shape, the fuel and moderator goes to infinity in the plus z and minus z direction. It goes to plus infinity and minus infinity in the y direction. The only variable is in the plus and minus x direction. As you might by common sense expect, the flux would be the largest value on the center line, and it would fall off symmetrically as you move away. And we said initially that we expected it to be a parabolic shape. This is just due to logic. When we solved this equation. So we're going back and we're going to make this substitution for here. So this general diffusion equation then becomes we then looked at the solution to this. So this is the solution to this equation, which is derived from the general equation by making it an infinite slab. We then use boundary and initial conditions to take this general solution to a specific solution. And that solution was the flux, which is a function of x, is equal to flux max times the cosine of pi x over x sub 0. So this is the specific solution for an infinite slab. If we go back to some of the geometries that we had, we know that this is the geometric width of all the materials. So that's x of g. Since x is equal to 0 right here, this is where flux max will occur, is on the center line. Of particular interest is where this boundary is, so this is going to be plus x of g over 2. We're interested in that boundary, which is minus x of g over 2. We notice that the flux does just not stop at the boundary. If you look at the solution to this equation, it actually goes to a point symmetrically outside. So this is where the flux goes to 0. This is where the flux goes to 0. And if we look at that dimension, that is x of 0, which is the point to where the flux goes to 0. So this is plus x of 0 over 2. This is minus x of 0 over 2. And again, x of 0 defines where the flux goes to 0. If you look at this little distance that exists between the geometric boundary of the fuel and where the flux goes to 0, that little value is d. It's the same on both sides. That little d is the extrapolation distance. So that if you look at the geometry, x of 0 is equal to x sub g plus 2d. And we have set it up this way so that we can use boundary and initial conditions to solve, or to solve this, to come up with this, and then to apply this to whatever we have. Any questions on where we sort of stand with that right now? Any questions on anything? Okay. So,
Professor, how do you get the value of D? It says D equals, I can't even read what that says next to it, but how do you get the value of D?
okay. We're going to go over that in just a second.
Okay.
I haven't told you yet how you find x of 0, x of g, and then how you find d. That's the next step I'm going to do right now. Okay. So, any questions on how we took the general diffusion equation, made it a specific diffusion equation for an infinite slab, solve that, and then we're going to ultimately use boundary and initial conditions to apply it. So, I'm going to leave this here and see if I can work around that. If you looked in the textbook, they derived an expression for buckling by taking this, using boundary and initial conditions and logic, and they came up with what buckling is, and this buckling is due only to shape. So, whenever you think infinite slab, hopefully the first thing that comes to your mind is buckling is equal to this. This relationship between buckling and shape is unique to the infinite slab. But if you remember back when we just looked at the materials, we also learned that buckling squared was equal to K infinity minus 1 over L squared. So, this one was due to materials. This one is due to shape. But buckling is buckling, so this is how through buckling allows us to couple the materials used to a shape. So that's really nice to have. This particular orientation is only good for an infinite slab. When we go to something else, such as a rectangular solid, a cube, a sphere, a cylinder, anything else, we will have a different relationship for buckling. Okay. So let's use that to our advantage. So we have the buckling squared is equal to pi over x sub 0 squared for an infinite slab. So if I take the square root of both sides, buckling is equal to pi over x sub 0. In our quiz, we're going to use the materials of beryllium, uranium-233, uranium-238, and we know that that buckling value was 0.206 centimeters to the minus 1. So now we have one equation, one unknown. So x 0 in this particular case is going to be pi divided by 0.602 centimeters to the minus 1. When you solve that, I had that value come out to be 15.3 centimeters. Now, the few I looked at, some of you did not carry over. Remember, we standardized when we solved it, just like we did for K infinity. We're going to use that same value all the way through this, because if you got a slightly different value, it's going to make your other answers be slightly off. So in this particular case, we know that B sub 0, this dimension is 15.3. If you go back to earlier in the chapter, and I'm going to erase this part now. We had a relationship that little d was equal to 0.71 divided by the macroscopic cross-section for transport. If you remember, the macroscopic cross-section for transport was something that we calculated back when we initially found buckling. We found this value, and we found the macroscopic cross-section for absorption. So since we've already found that value, we can go back and use it. So this was 0.71 divided by 0.7825. So I had that value come out to be 0.91 centimeters. Okay. So if we go back to our expression that x sub 0 is equal to x and g plus 2d, then x sub g is equal to x sub 0 minus 2d if we move this over on the other side. We know this value, and we just calculated little d. So I had that value come out to be 13.48 centimeters. So this value is 13.48 centimeters. This little d is 0.91. This little d is 0.91. Any questions on how we did that? Okay. Now comes to the part that everybody seems to get tripped up on. When I gave you that the flux max was 15 times 10 to the 15th neutrons per square centimeter per second, and I told you this is thermal. Okay. If we go back to the solution, we know that this is a solution to an infinite slab, so we can substitute this value back in. Now you can go ahead and substitute a value back in here if you want to. So you could have gone back and said, okay, I know x of 0 is this value. So that's certainly acceptable. Cosine of pi x divided by 15.3. In this particular case for the quiz, you would have probably made out better, rather than doing that, just leaving it this way, because I asked you to find the flux at...
Professor, I have a question. In the quiz that you gave us the flux value, and it was 5 times 10 to the 15th, not 15 times 10 to the 15th.
Thank you. I wrote it, my solution correctly, I wrote it up there incorrectly. Okay. But I would have caught myself in a minute, but thank you anyway. Okay. So I ask you, what is the flux at x is equal to minus x of 0 over 3? So if you look back at here, what I'm doing is x has a minus value, so it's going to be on this side of the center line. And I know that it's going to be, what is the flux somewhere on this side? And what I'm asking is, what is the value of this equation? And this plots like this blue line. This blue line is flux is a function of x. So I'll make it a green line just to keep the colors consistent. So we know that this is minus. It's going to be some point here, and you're actually going to be finding that value. So if we go back and apply that, the flux at minus x of 0 over 3 is equal to 5 times 10 to the 15th cosine of pi. What is x? We're saying x is minus x of 0 over 3 divided by x of 0. Cancel, cancel. So this says my flux is equal to 5 times 10 to the 15th times the cosine of minus pi over 3. Now, whenever you have a trigonometric function, and this is where some people went awry, in this particular case, if I tell you that we have the cosine of pi over 3, how do we treat that pi? What is the value of that pi value? What is it?
Professor,
Yes.
can we go back to where you wrote on the left side of the board? You had the flux of negative x sub 0 over 3. Can you read that line to us, please? I can't read what you wrote.
Is equal to the flux max, which is 5 times 10 to the 15th, times the cosine of this expression, which is pi, and then I substituted for x what we're using, which is minus x of 0 over 3, and then I'm putting in x of 0 again. So if I blow that up, we had pi times x over x of 0. What I did is I went back and I said, we know for this particular case that x is in fact minus x of 0 over 3. I'm making that substitution. Then I have x of 0 here, x of 0 there. I can cancel those two out. So what I have now is minus pi over 3. So I made this equation now.
I see it
X
now.
is equal to 5 times 10 to the 15th times the cosine of quantity minus pi over 3. Then I'm going back just for general understanding. When we have the cosine of pi over 3, how do we treat that pi? What is that value? Remember, this is a trigonometric function. So how do we treat pi? Anybody? If it's a trigonometric function, we treat pi as 180 degrees. Yeah. So this is going to become the cosine of 180 over 3, and that's going to become the cosine of 60 degrees. So this becomes the flux at minus x of 0 over 3 is 5 times 10 to the 15th times the cosine of minus pi over 3, which is the cosine of minus 60. And I had that value come out to be, come out wherever you are. One half. So the flux at the point of interest is 2.5 times 10 to the 15th neutrons per square centimeter per second. So that means at wherever this point is here, this is minus x sub 0 over 3. If I go directly up, because remember, this equation plots like this green line. So that is the value of the flux at that point. Everybody with me? Anybody lost? Okay. So we solved that. A lot of you ended up treating this pi as 3.1416. You can't do that. Pi in this shape is used outside trig functions. And we're going to see where that comes into play in just a minute when we do the neutron current density. Any questions on what we've done so far? Okay. So I'm going to save over here that the flux at minus x of 0 over 3 was 2.5 times 10 to the 15th. All right. So now I'm going to go back and erase all this. Okay. And now I ask you, what is the neutron current density in the minus x direction at x? Remember, this is a function of x. In this particular case, I'm saying, what is the neutron current density in minus x direction at our minus x of 0 over 3? We know that our equation, I'll just leave it x for right now, is evaluated at some point is equal to the flux at that point divided by 4. If this is a minus, this is a plus, 1 over 6 macroscopic cross-section for scattering times the partial of the flux with respect to the axis of interest, which in this case is x. And again, we're evaluating that at the point 0. So this is what the neutron current density is in the minus x direction. And all we're going to do now is substitute in a value of x and go from there. Now, this first part of the equation is no problem because we know that this x of 0, we just found that is 2.5 times 10 to the 15th. Because this is the flux at the point of interest. Okay. Now we look at this. What is this? Macroscopic cross-section for scattering is the number density times the microscopic cross-section for scattering. And if you remember back last week or maybe the end of the previous week, we calculated this value when we were finding P, which was the resonance escape probability. And if you remember, this has 3 parts because we have beryllium, we have uranium-233, we have uranium-238. So if you kept your notes, you could go back and say, aha, I'm ahead of him. I know what that value was earlier, and I can just go and substitute that in. But if you look at how they utilized or applied that equation later, in that development of neutron current density, you would see that this became big D over 2 times the partial of the flux with respect to x evaluated at the point. So this is equal to that, where D is defined as diffusion coefficient if you also looked at the development of the problem that they had when they found what x of g and x of o and d was, you would see that little d is equal to 2 big D, or big D is equal to little d divided by 2. So I can go back in this expression. Now I know I could have either substituted in the macroscopic cross-section for scattering, or I could have realized that this relationship is equal to that relationship, and then realizing this relationship, come up with this, so that this becomes little d over 4. So we started out with this, we came to an intermediate, and then we finally came to this. But we know what that value is. So if I go back up here, this has become little d over 4, but I know little d is 0.91 from earlier in this problem. So I have almost everything I need now except this guy. Okay? And what is this? This is the partial of the flux with respect to x, because it's an infinite slab, it only varies in that direction. And we're evaluating this at the point of interest. So we have to first of all go back and what is the flux equation? It's that. Okay. We now want to differentiate this with respect to x, which means we have to differentiate this side with respect to x. So this becomes, and I'm actually interchanging these. Technically, it is this, the partial of the flux with respect to this one variable, but in this case, it only varies in the x direction, so this is also this, a sort of straight little d. So if I take the partial of this with respect to x, that's a coefficient, so we leave that as is. Then I'm going to differentiate this, and if you differentiate this, it becomes minus the sine of pi x over x of 0 times you differentiate what's inside. So the differentiation of this becomes just this. Okay. So this is the differentiation of that. We're going to substitute that back into here. But when we do that, we're going to evaluate this at the point of interest because we're interested in what is happening right here. Okay. So let me go back and do that. So this becomes 5 times 10 to the 15th times minus the sine of pi, and what's x? X is minus x sub 0 over 3 divided by x sub 0 times pi over x sub 0. So this becomes 5 times 10 to the 15th times minus the sine of, again, cancel, cancel, minus pi over 3 times pi divided by x sub 0. If we go back now, this is minus the sine of minus 60. This pi, how do we treat that? That is outside of trigonometric function. So this pi is 3.1416. What is x sub 0? From our initial work we did at the start, that value was 15.3. So if you evaluate all of this with these numbers, that substitutes in for this, because that is the partial of the flux with respect to x, evaluated at our point, which was x sub 0 over 3. When I did all that algebra, I came up with at minus x sub 0 over 3, because that's the value for x. I had this value, the 2.5 times 10 to the 15th divided by 4. I had that guy come out to be plus 0.625. When I multiplied this times this, times this, times this, times this, I had that total come out to be plus 1.032. I add those two guys together and I came up with 1.66. And the units are, just like flux, neutrons per square centimeter per second. And that is the value in the minus x direction at that point. So if we go back to this point, I put my little window right here, and I'm looking at what is going through the window perpendicular to the window in that direction, and that is jx minus at that point, and that is that value. Now, where most of you in the, well, I shouldn't say most of you, in the few
Professor,
examples that I looked at, the
right?
quiz, say that again?
Professor, on the right, the bottom right-hand corner where you did the derivative of the flux over the derivative of x, could you please rewrite that larger and in a darker color? Or say it again, just because we can't really read it.
Let me write it. Let me rewrite it. Let me see if I can sandwich it in here. Looks like we've got most of you. Can you see and hear me okay?
Yes.
Yes.
Okay. I'll give maybe one more minute, then I'm going to start up again.
While we're waiting, can I ask you a question?
Sure.
Is it possible for you to scan and send out the work that you did for this quiz to all of us so we can see it all in one spot?
Okay, yes. I'll do that later today.
Okay, thank you.
Okay, so let me go ahead and get started because we do have a limited amount of time. What I'm going to do is I'm going to go back to just this part again. So I'm going to erase this. Okay. So what I'm looking at is I'm taking out of that one equation the partial of the flux with respect to x, and we're evaluating it at some point. Now, since this is an infinite slab, this is really this. This one tells you that the flux could vary by a number of different variables. That's why you have the script D. When you have the regular D, it means the only thing the flux varies with is x. So if I wrote the equation, I would write it like that to show that it only varies that way. So I'm looking to do that, and we know that the flux is equal to 5 times 10 to the 15th neutrons per square centimeter per second times the cosine of pi x over x sub 0. If we go and take the partial of this with respect to x, that means we have to do the partial with respect to x on that side. So when we do that, this is a coefficient, so that stays the same. Okay. Then when we differentiate the cosine of pi x over x sub 0, when you differentiate the cosine, it becomes minus the sine of whatever this is. Then you differentiate what is inside that cosine function. So if you differentiate this part, it just becomes pi over x sub 0. Okay. So the partial of the flux with respect to x is this. Again, this is the coefficient. We've differentiated the cosine to come up with this part, and then you have to differentiate what is inside the cosine term, and we've come up with that part. Now we want to evaluate this at the point of interest, which is where we're evaluating it at. So my x is going to be then minus x sub 0 over 3, because that's the point I'm evaluating it at. So again, this cancel becomes minus the sine of minus pi over 3. We know pi over 3 is 180 divided by 3, which is 60. So this becomes minus the sine of minus 60 degrees. This part becomes pi over x sub 0 was 15.3 back when we did the original work. Okay? So, in this particular case, this pi, since it's not in a trigonometric function, this becomes 3.1416. It's only 180 degrees if it's in a trigonometric function. So when I did all the math on this part, I came up with the answer that I put on the board before. I know that was a quick go over. Does anybody have any questions on that? I could do another one real quick.
So, Professor, you said that on the board you got 1.66. Is that correct?
I got, if we go back to the whole thing, let me erase all of this. We started out that the neutron current density in the x direction, we want to evaluate it at some point. It's equal to the flux at that point divided by 4. This is a minus, this becomes a plus. And then we showed you how that evolved to be little d over 4 times the partial of the flux with respect to x evaluated at the point of interest. This guy from before was 2.5 times 10 to the 15th divided by 4. I had that come out to be 0.625 plus d was 0.91 divided by 4. And then we had the partial, and that was, we did this, was 5 times 10 to the 15th times minus the sine of minus 60 degrees times pi over x of 0, but x of 0 was 15.3. So when I did all of this, I had that value come out to be 1.032. Added this to this.
Professor, what happened to the 10 to the 15th? I mean, 2.5 times 10 to the 15th divided by 4. I mean, maybe there's something I'm not getting, but.
For this?
Yeah. Okay, so it's the 1.6 times 10 to the 15th. Okay.
Yes. So all of these, when you add them up, it's going to be times 10 to the 15th. Neutrons square centimeter per second. So that is the value of the neutron current density at this point going in that direction through our little window. If I'd ask you what is the neutron current density in the plus x direction at this little window, what would change? You're still evaluating at the point, so you'd have the little 0 here, the little 0 here. This stays the same, this stays the same. The only thing that changes is this, if this is a plus, becomes a minus. But this is the same, all of this is the same. It's only this part that becomes a minus. Are you getting that, or would you like me to do another one? Or do you think you have that?
If you could do another one, that would be great.
All right. Let's, actually, I had planned to give you a quiz, but I don't know if I'm going to have enough time to cover that. Let me try to do this. I'm going to try to take this to the next step up, which is doing a rectangular solve. And we might slip a little bit into Professor Lance's time, but I wanted to give you a feeling of how this works. So bear with me on this. So I'm going to erase all of this. Let me go back, and in this case, let's say we're going to put our material in a rectangular solid. And in that case, we know we're going to have X, Y, and Z for variables. To solve this, we still have to go back to the general diffusion equation. We have to solve this for a rectangular solid. And for a rectangular solid, the del 2 operator is so if we apply this to our equation, this becomes we then have to solve this general diffusion equation using boundary and initial conditions to come up with our specific diffusion equation. Okay. If you did that, and they do it for you in the book, so I'm just going to take a shortcut here. Flux, because it's three-dimensional solid, varies by X, Y, and Z. And when you solve all of those boundary and initial conditions, this equation comes out to be flux max times the cosine of pi x over x sub 0 times the cosine of pi y over y sub 0 times the cosine of pi z over z sub 0. Okay. Also, when you solve that, you will find out that buckling squared for a rectangular solid ends up equaling pi over x sub 0 squared plus pi over y sub 0 squared plus pi over z sub 0 squared. So whenever you solve putting fuels and moderators into a three-dimensional rectangular solid, this is how you define buckling. And again, this is relating shape only. But you also know that buckling for materials is equal to k infinity minus 1 over L squared. So this is equal to this is equal to this, therefore this is equal to this. Right? And then you could solve things. Now, when you solve this, you're going to come up with this equation. And just for exclamation right now, I'm going to pretend that you've used boundary and initial conditions, and I've given you a flux. And now we're going to see how we would solve the other problem. So, let's say for the materials that I've given you, the flux is a function of x, y, and z is equal to 8 times 10 to the 18th neutrons per square centimeter per second times the cosine of pi x over 20 times cosine of pi y over 15 times cosine of pi z over 25. This is the equation for flux as a function of a position within a rectangular solid. If I ask you, what is the flux at a particular point? Let's say, what is the flux at 5 minus 3 and 5. So x is equal to 5, y is equal to minus 3, z is equal to 5. I'm looking to see what is the flux at that point. So I go back to this equation, and wherever I see an x, I put a 5. Wherever I see a y, I put a minus 3. Wherever I see a z, I put a 5. So this thing reduces to 8 times 10 to the 18th times the cosine of 5 into this would be the cosine of pi over 4. This becomes the cosine of minus pi over 3. This becomes the cosine of pi over 5. Okay. This is 180 degrees, so this guy comes out to be cosine of 45 degrees. Pi is 180 degrees, so this becomes a cosine of minus 60. This is 180 degrees, so this becomes a cosine of 36. So this has become 8 times 10 to the 18th times the cosine of 45 degrees times the cosine of minus 60 degrees times the cosine of 36 degrees. You know how to get a number for this, get a number for this, get a number for this, multiply it times that, and that is now the flux at the point of interest, which is 5 minus 3, and 5 is equal whatever number you got for that. Again, times 10 to the 18th neutrons per square centimeter per second. Let's say I then ask you, what is the neutron current density? Pick a direction. Somebody pick a direction for me.
Z. Positive Z
Plus or
direction.
Z plus or minus?
Plus.
Plus. So we want to know what is the Z, what is the neutron current density in the plus Z direction at our point of interest. So I could even write that in, 5 minus 3 and 5. We know that the governing equation for neutron current density is the flux at the point divided by 4. If this is a plus, this has to be a minus. Little d over 4. There's other variations. You could use capital D. You could use a macroscopic cross-section for scattering. This is the easiest one. Times, now it's a true partial of the flux with respect to Z, since we're looking at Z. And we have to evaluate it at the point of interest. Okay. What is the flux evaluated at the point? We just found that value up here, so I'm just going to use that number. Everybody with me on that? What is D? You will have found the little d the same way that we did before. So it's whatever this value is. Okay. Now we have to look at the partial of the flux with respect to Z. So the flux again is 8 times 10 to the 18th times the cosine of pi x over x sub 0, cosine of pi y over y sub 0, cosine of pi z over z sub 0. I then am going to take the partial of this just with respect to z. When you do that, you're going to do that to this side also, because that's what you have to do to keep the equation the same. So this means I'm only going to differentiate this with respect to z. When I do that, everything that is not z remains constant. So this becomes eight times 10 to the 18th. This stays the same because there's no z. This stays the same because there's no z. Then I'm looking at this guy. So I need the partial of the flux with respect to z for just this part. Okay. And just like we did before, when you differentiate the cosine, it becomes minus the sine of whatever it is. Then you have to differentiate what's inside the cosine part, which is going to be just pi over z sub 0. So this is this, which would go in here. And we want to evaluate this at the point of interest, which we know is 5, minus 3, and 5. So you go back here, you'll have already had these values. You know what those are. You put those in. So wherever you have an x, you'd put a 5. Wherever you have a y, you'd put a minus 3. Wherever you have a z, you'd put a 5. Pi, when it's outside, again, is 3.1416. Pi, when it's inside any trigonometric function, is 180 degrees. So you have everything you need to evaluate this at the point of interest. That goes back into this equation because that's what you need there. You do some number crunching, and then you have the neutron current density in the plus z direction at this particular point of interest.
Okay, and what are we using for the denominator in those fractions for all the cosines?
You mean here?
I mean, everywhere there's a fraction for a cosine.
Okay.
Like, what are we putting in for x sub naught and y sub naught?
Remember, I originally gave you what I had. I had x sub 0 was equal to, I think it was 20. Y sub 0 was equal to 15, and z sub 0 was equal to 25 when I originally
Oh, okay.
said.
I missed that part. Thank you.
Okay. So you just go back in and you put in the values. When you come back up here, this x is going to be this value because this is varying with x, y, and z. So wherever you see an x, you put this. Wherever you see a y, you put this. Wherever you see a z, you put this. If you need to put in an x sub 0, y sub 0, or z sub 0, you're going to use those values. And then whenever the dust settles and you've done all this math, you will have the neutron current density at this point. Whatever that number is the neutron current density, neutrons per square centimeter per second. And again, this is in the plus z direction. So in essence, our little window is right here, 1 centimeter divided 1 centimeter. And we're looking at what is coming out, in this case, in the plus z direction, which would be into the room. To think about this a little bit further, I have found what the Z plus neutron current density is. I could ask you, what is the neutron current density in the Z direction, which would be the difference in, for this little window, what's plus Z going in this direction, what's minus Z going in that direction. Whatever that difference is the net neutron current density through that little window. So that's telling you, if you want to think of it, leakage going through that little thing. I could do the same thing for Y, except this time my little window would be in this direction, plus Y minus Y. I could do the same thing for Z. Well, I did Z for X. Okay. So now I have a value for X, Y, and Z. We know these are three vectors. We know that they are mutually orthogonal. So if I look at the overall neutron current density at a point of interest, it's going to be what's happening in the X direction, what is happening in the Y direction, what is happening in the Z direction. These are each vectors, and we have to add them vectorially. Remember when we started off the semester, I got you to think three-dimensional? This is why I was getting you to think of that ahead of time. So if you would, wherever this is, we have a little 1 centimeter by 1 centimeter cube. And whenever you add this vector to this vector to this vector, you'll have the net neutron current density coming out of that cube. I could try to give you, in fact, I think I will give you a quiz. It'll be due on Monday. You're going to have to think about this a little bit. But I think you can do it. And what I'm going to do, and I know this is, hopefully you've covered some of this math before, like partial differentiations and whatever. That was erased before I could really read it. Whoever put that up, did you put it back up? Okay. Let me go back. I have a...
Professor, he wants to know what buckling is for a rectangular solid.
What buckling is for a rectangular solid?
Yep.
It is this. Buckling for any rectangular solid is whenever I tell you rectangular solid, automatically this is the buckling for that. And you would tie that back together to the materials to start to work the problem. So I'm going to give you a quiz. I'm going to send it out to you in the next couple of minutes. But what I'm going to do is I'm going to do a variation of that, and instead of a rectangular solid, I'm going to give you a specific rectangular solid, and I'm going to tell you that you have a cube. If you have a cube, then you know that x sub 0 is equal to y sub 0 is equal to z sub 0 is equal to x sub 0 again. You also know that x sub g is equal to y sub g is equal to z. We can take
Units
one
of
of them. Let's
Fahrenheit.
say x. So x sub 0 is x sub 0. Y sub 0 is also equal to x sub 0. Z sub 0 is also equal to x sub 0. And this is unique only for a cube. And if you look at this, if we add like terms, This is a like term, this is a like term, this is a like term. My buckling squared becomes 3 of these guys. Okay. So I can relate this back to whatever I had for materials, which we've already calculated that value from whatever that was before. Like I think the sample we had, that was what, 0.26? Okay. So we could place our materials that we've just been working with beryllium. We have buckling. We can relate that back to this. You can solve this for x of 0, and you know that that's equal to this is equal to this is equal to this. D is the extrapolation distance. It does not change. So no matter what shape you have it in, D is always D. So I'm giving you this hint up front. The quiz that I have is based on solving information for a cube. So I'd like for you to try that. The quiz will be due before the start of Monday. I plan to get into some nuclear material science today and to start looking at multiple bending axes rather than just one, but obviously I'm not going to have time for that, so I'm not going to give you a quiz in that. I will, when I get back to the office, I will scan to you my solution for the quiz that was due today. I'm going to have to redo this to make sure, because I can read my writing. I want to make sure you're able to read my writing. I will send you that today. The quiz will be due at the start of class on Monday. I have most of you right now. I will hang around for a little while today because we have power back. In fact, it wasn't going to be too much longer where without any lights, your offices and everything are dark. Does anybody plan to see me on anything today after Professor Lance's class? Anything, whether it's registration, plan of study, anything. Does anybody plan to see me today? Okay, I will grade the quizzes that I took today. I have the other quizzes that you gave me on Monday. So all of those will be graded and in the box before I leave tonight. I will not be in tomorrow. I'll be out of state all day, get back very late. Monday, I'm not sure if I'm going to be in, but if I am in, it'll be in the afternoon after 1 o'clock. And then, of course, I'll be back in on Monday. So, yes, I'm going to, of course, substitution book. So if you want to hang on 1 second. I thought I was going to be able to go back and send you the quiz, but I've got to restart that computer again to get back to that page, I think. Hang on 1 minute. I might be able to get in real quick. Nope, it's not going to let me do it. All right. I will send you the quiz for reactor theory. Again, it's for a cube. I've given you this hint to start with. Hopefully you can pick up from what we did on the board today. That'll be due on Monday. I will grade that one liberally since we didn't get through everything I wanted to cover today for rectangular solids. And then when we start next week, we're going to take it to look at other things like putting that material into a sphere, putting it into a cylinder. We can put it into any shape we want as long as we can define what the buckling squared is for that unique shape. So there's a unique one for spheres, there's a unique one for cylinders, and any kind of shape you could come up with, there is a buckling squared value or expression for that. So let me let you go now. I will have email when I get back. I will send you, as soon as I get back to the office, I will send you the quiz due Monday, I will do the quiz solution and I'll also send you the course substitution form. Do you have anything else for me right now?
I just have a quick question that I want to ask. So we have the equation is b squared equals pi over x, y, and z squared. So, but if we just use our buckling number, we just get rid of, we basically take the square root of everything. Is that correct? So b would just equal pi over x is not plus.
So this, so this is so if you take the square root of this to come up with b, okay, what you're taking is the square root of this entire side. You just can't do this one by itself, add it to this one by itself, add it to this one by itself, if you understand what I'm saying.
Okay, yes, no, I do. Thank you very much. So we just have to make sure we use b squared and not just the buckling.
That's right. This is not, in other words, you can't just take the square root of this one, add it to the square root of that one. That is not true. You have to do the entire expression. That's why I made it easy for you by making it a cube, because then this is equal to this is equal to this, and you came up with this expression, which you can take the square root of both sides then and find that guy. You with me, Tony?
I'm with you. Yeah, thank you. I appreciate it.
Any other quick questions? Okay. Again, if you want me to see me for anything today, I'm willing to stay. But all I have to do right now is send you out those 3 things, grade the quizzes you gave me today. And if I don't hear from anybody, I'll probably leave by 5:30 today. Or maybe before if I finish up everything. Good luck on that. And hopefully you can tell the others when you're in Professor Lance's class what I'm sending out, because not everybody is here right now. Okay, thank you for coming back in. And I'll see you Monday at the latest. Take care.